You have learnt that if a line L passes through the origin in three-dimensional space, making angles alpha, beta, and gamma with the positive directions of the x, y, and z axis respectively, then the angles alpha, beta, and gamma are called directional angles of the directed line L. The cosines of the directional angles of a directed line are called its directional cosines. Thus, cos alpha, cos beta, and cos gamma are the direction cosines of directed line L. By convention, the direction cosines cos alpha, cos beta, and cos gamma are denoted by the letters L, M, and N respectively. Note that a line can be extended in two directions in space. If we consider the opposite direction of line L, then the angles made by the line with the x, y, and z axes are supplementary angles to alpha, beta, and gamma respectively. In this case, the direction cosines of line L are minus cos alpha, minus cos beta, and minus cos gamma respectively. Hence we can say that every line in space has two sets of direction cosines. To find the direction cosines of a line that does not pass through the origin, we consider a line parallel to the given line and passing through the origin. Since the two lines are parallel, the angles made by them with the coordinate axes are equal. Therefore, the two parallel lines have the same direction cosines. Now, let us derive a relationship between the direction cosines of a directed line. Consider a line L in space. Draw a line L1 parallel to line L and passing through the origin. Consider a point P with the coordinates x, y, and z on line L1 such that its distance from origin O is r. This gives the relation x square plus y square plus z square is equal to r square. Let this be equation 1. Let PA, PB, and PC be the perpendiculars drawn from point P onto the x, y, and z axis respectively. Therefore, the lengths OA, OB, and OC are x, y, and z respectively. Let alpha, beta, and gamma be the angles made by line L1 with the positive directions of the x, y, and z axis respectively. Thus, the direction cosines of the given line are cos alpha, cos beta, and cos gamma. In right-angled triangle OAP, cos alpha is equal to OA upon OP, or x upon r. This gives us equation 2. Similarly, finding the value of cos beta from right-angled triangle OBP, we get equation 3. The value of cos gamma from right-angled triangle OCP gives us equation 4. Adding the squares of x, y, and z from equations 2, 3, and 4, and simplifying, we get equation 5. Substituting the value of r from equation 1 in equation 5, we find that the sum of the squares of the directional cosines of the given line L is 1. While deriving the relation between the direction cosines of a line, we arrived at 3 equations as shown. the expressions LR, MR, and NR represent a number triad that is proportional to the direction cosines L, M, and N of the given line. Any three numbers that are proportional to the direction cosines of a line are called the direction ratios of the line. By convention, the direction ratios of a line are represented by the letters A, B, and C. Since direction ratios are proportional to direction cosines for any non-zero real number lambda, we can express direction ratios in terms of direction cosines as shown. A line can have infinite sets of direction ratios corresponding to different values of lambda. Let us now derive a relation between direction cosines and direction ratios of a line. The ratio between the direction cosines of a line and its direction ratios is constant. Let this constant be k. Equating each term of the previous equation with the constant k, we get the three equations as shown. Squaring and adding the values of the direction cosines of the line from equations 1, 2, and 3, and simplifying, we get equation 4. We already know that the sum of the squares of the direction cosines of a line is equal to 1. Substituting this value in equation 4 and simplifying, we get the value of k as shown in equation 5. Substituting the value of k from equation 5 in equations 1, 2, and 3, we get the relation between the direction cosines in terms of the direction ratios of the line. The sign for the direction cosines is taken as positive or negative depending on the desired sign for the constant k. Now, we will derive a formula to find the direction cosines of a line passing through two given points. Consider a line passing through two given points A and B as shown here. Let us find the direction cosines of this line. Draw a line passing through the origin and parallel to the line passing through the given points A and B. Let alpha, beta, and gamma be the angles made by the line passing through the origin with the positive direction of the x, y, and z axes as shown. Thus, the direction cosines of the given line are cos alpha, cos beta, and cos gamma. Draw a perpendicular BQ from point B to the xy plane. Now, draw a perpendicular AC from point A to BQ. From the two similar triangles shown in the figure, we find that angle BAC is equal to angle beta. In right-angled triangle BAC, cos beta is equal to AC upon AB. Let this be equation 1. From the figure, AC is equal to y2 minus y1. Using the distance formula, we get the value of AB as shown. Substituting the values of AB and AC in equation 1, we get the value of cos beta as shown. Similarly, we can find the values of cos alpha and cos gamma. Using these equations, we can find the direction cosines of a line passing through given 2 points with the coordinates x1, y1, z1, and x2, y2, z2. We can also find the direction ratios of a line passing through two given points as shown here. Consider a point A with position vector A with respect to the origin. Let vector B be any vector in space. Consider a line is passing through point A and parallel to vector B. Let us derive the equation for line L in vector form. Let P be any arbitrary point on line L. Let the position vector of point P with respect to the origin be vector R. Since the given line L is parallel to vector B, we can say that vector AP is also parallel to vector B. This implies that vector AP is equal to a scalar multiple of vector B. Let this be equation 1. Applying the triangle law of vector addition to triangle OPA, we get vector AP equal to vector R minus vector A. Let this be equation 2. Equating the values of vector AP from equations 1 and 2, we get equation 3. Equation 3 is the vector equation of a line that passes through a point with position vector A and is parallel to vector B. Now, let us derive the equation for line L in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus, we can write the position vector of point A as shown. Similarly, let the coordinates of point P be x, y, z. Thus, we can write the position vector of point P as shown. If the direction ratios of line L are given, we can find vector B that is parallel to line L as shown. Note that B is the direction ratio of line L along the y-axis and not the modulus of vector B. Also note that if vector B is given in its component form, then we can find the direction ratios of line L as shown. Substituting the values of vectors A, R and B from equations 4, 5 and 6 in equation 3, we get equation 7. Simplifying equation 7 and equating the coefficients of unit vectors I, j and k, we get the equations for x, y and z as shown. Eliminating lambda from the equations for x, y and z, we get equation 8, which is the Cartesian equation of a line that is parallel to a vector having direction ratios A, B, C and passes through points x1, y1, z1. If L, M and N are the direction cosines of the line, then the Cartesian equation of the line is of the form as shown. We can also determine the equation of line L if it passes through two given points. Let us first derive the equation for line L passing through two given points A and B in vector form. Let the position vectors of points A and B with respect to the origin be as shown. Let P be any arbitrary point on line L with position vector R. Since points A, B and P lie on the same line, vector AB and vector AP are collinear. This implies that vector AP is equal to the product of vector AB with a real number lambda. Let this be equation 1. Applying the triangle law of vector addition to triangle OAP and simplifying, we get the value of vector AP as shown in equation 2. Similarly, from triangle OAB, we get the value of vector AB as shown in equation 3. Substituting the values of vectors AP and AB from equations 2 and 3 in equation 1, we get equation 4. Equation 4 is the vector equation of a line that passes through 2 points with position vectors A and B. Now, let us derive the equation for line L in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus we can write the position vector of point A as shown. Similarly, if the coordinates of point B are x2, y2, z2, we can write the position vector of point B as shown. If the coordinates of point P are x, y, z, we can write the position vector of point P as shown. Substituting the values of vectors A, B, and R from equations 5, 6, and 7 in equation 4, we get equation 8. Simplifying equation 8, and equating the coefficients of unit vectors I, j, and k, we get the equations for x, y, and z as shown. Eliminating lambda from the equations for x, y, and z, we get equation 9, which is the Cartesian equation of a line that passes through 2 points with coordinates x1, y1, z1, and x2, y2, z2. Consider 2 lines, L1 and L2, passing through the origin as shown. Let theta be the acute angle formed between lines L1 and L2. You will learn to find the value of this angle theta using the direction ratios, direction cosines, vector equations, or Cartesian equations of the 2 lines. Consider a point A on line L1 and a point B on line L2. Now, consider the directed lines OA and OB, representing the position vectors of points A and B, respectively, with respect to the origin. Let A1, B1, C1, and A2, B2, C2 be the direction ratios of lines L1 and L2 respectively. Thus vectors OA and OB can be written in component form as shown. We know that the cosine of angle theta between 2 vectors is given by their dot product divided by the product of their magnitudes. The dot product of vectors OA and OB is equal to the sum of the products of their corresponding components as shown here. The magnitude of vectors OA is equal to under root of A1 square plus B1 square plus C1 square. Similarly, the magnitude of vector OB is equal to under root of A2 square plus B2 square plus C2 square. Substituting the values of the dot product of vectors OA and OB and their magnitudes in the expression for cos theta, we can find angle theta between lines L1 and L2 in terms of their direction ratios. Let this be equation 1. Now, we will find the sine of angle theta between vectors OA and OB. From trigonometric identities, we know that sine theta is equal to under root of 1 minus cos square theta. On simplifying, we get the expression for the sine of angle theta between lines L1 and L2. Let this be equation 2. These equations lead to some interesting observations. If lines L1 and L2 are perpendicular to each other, then the value of theta is 90 degrees and cos theta is 0. Equating the value for cos theta to 0 from equation 1, we get the condition for the perpendicularity of two lines. If lines L1 and L2 are parallel to each other, then the value of theta is 0 degrees and sin theta is 0. Equating the value for sin theta to 0 from equation 2, we get the condition for two lines to be parallel as shown here. The given lines L1 and L2 may not always pass through the origin. In such a case, we find the angle between them by considering lines L1' and L2' that are parallel to L1 and L2 and pass through the origin. Now, let us see how we can find angle theta if we are given the direction cosines of lines L1 and L2 instead of their direction ratios. If L1, M1, N1 and L2, M2, N2 are the direction cosines of lines L1 and L2 respectively, then from equation 1, cos theta can be written as shown. Let this be equation 3. We know that the sum of the squares of the direction cosines of any line is always equal to 1. Thus, the terms in the denominator of the right-hand side in equation 3 is reduced to 1. Equation 4 gives us the equation for the cosine of angle theta between lines L1 and L2 in terms of their direction cosines. Replacing the direction ratios with direction cosines in equation 2 and simplifying, we get the equation for the sine of angle theta between lines L1 and L2 as shown here. Now, we will find the angle between the two lines when their vector equations are given. Let us represent the two lines L1 and L2 with their vector equations. Let the vector equation of line L1 be vector A1 plus lambda into vector B1. Similarly, let the vector equation of line L2 be vector A2 plus mu into vector B2. The cosine of angle theta between the two given lines is equal to the modulus of the dot product of vectors B1 and B2 divided by the product of the magnitudes of the vectors B1 and B2. Let us now find angle theta using the Cartesian equations of lines L1 and L2 shown here. From the Cartesian equations of the given lines, we get that A1, B1, C1 and A2, B2, C2 are the direction ratios of the two lines. Thus, the cosine of angle theta between the lines given in Cartesian form can be found using the formula shown. Before we start the discussion on finding the shortest distance between a pair of lines, let us take a look at some types of pairs of lines. First, consider a pair of coplanar lines L1 and L2. Two lines lying on the same plane can either be parallel or intersecting. Thus, there are only two possibilities in case of a pair of coplanar lines. They can be either parallel to each other or intersect each other at a point. Now, consider two non-coplanar lines, like lines L1 and L2, lying on different faces of a cuboid. Now we have a number of possibilities. Two non-coplanar lines can be a pair of parallel lines. Two non-coplanar lines can be a pair of intersecting lines. You can also have a pair of non-coplanar lines that are not parallel and still do not intersect each other in space. Two lines that are neither parallel nor intersecting are called skew lines. Note that skew lines are always non-coplanar. Since they are not parallel, they will intersect each other if they lie on the same plane. Observe that intersecting lines meet at a point. Thus, the shortest distance between two intersecting lines is 0. Now, you will learn to find the shortest distance between a pair of skew lines and a pair of parallel lines. Let us start with finding the shortest distance between a pair of skew lines. The shortest distance between two skew lines is the length of the shortest line segment that joins a point on one line to a point on the other line. For skew lines, such a line segment is perpendicular to both the lines. Consider a pair of skew lines L1 and L2, represented by the vector equations as shown. Here, A1 and A2 are the position vectors of points, say M and N, on lines L1 and L2 respectively. Thus, vector Mn is given by vector A2 minus vector A1. Let this be equation 1. Let vector AB represent the shortest distance vector between lines L1 and L2. Let the shortest distance between lines L1 and L2, or the magnitude of vector AB, be d. Thus vector AB is equal to d into unit vector n in the direction of vector AB. By definition, vector AB is perpendicular to both lines L1 and L2. This implies that vector AB is also perpendicular to both the vectors B1 and B2. Thus, unit vector n in the direction of AB is equal to the cross product of vectors B1 and B2 divided by the magnitude of their cross product. Substituting this value of unit vector n in the equation for vector AB, we get equation 2. Let theta be the angle between vectors Mn and AB. Thus, the projection of vector Mn on the shortest distance vector AB is given by equation 3. Cos theta is also given by the dot product of vectors AB and Mn divided by the product of their magnitudes. Let this be equation 4. Substituting the values from equations 1 and 2 in equation 4 and simplifying, we get equation 5. Comparing equations 3 and 5, we get the equation that gives the shortest distance between skew lines L1 and L2. The shortest distance between two skew lines, represented by Cartesian equations, can be calculated by the formula shown here. Now, let us find the shortest distance between a pair of parallel lines. Consider a pair of parallel lines L1 and L2 represented by the vector equations as shown here. Here, A1 and A2 are the position vectors of points, say P and Q, on lines L1 and L2 respectively. Thus, vector PQ is given by vector A2 minus vector A1. Let this be equation 1. Draw a perpendicular from point P on line L1 that meets line L2 at R. Now, vector PR represents the shortest distance vector between lines L1 and L2. magnitude d of vector PR is the shortest distance between the lines L1 and L2. Let theta be the angle between vectors PQ and vector B that is parallel to both lines L1 and L2. Thus, by formula, the cross product of vector B and vector PQ is represented by equation 2. Substituting the value of modulus of vector PR in the equation for sin theta, we get equation 3 as shown. Substituting the values from equations 1 and 3 in equation 2, we get equation 4 as shown. Taking the magnitude of the terms on both the sides of equation 4 and simplifying, we find the equation for the shortest distance between parallel lines L1 and L2. In space, it is possible to have an infinite number of planes passing through a given point or a line. We can determine a unique plane in space under certain conditions. These conditions give us different forms of the equation of a plane. Let us see what these conditions are. We can determine a unique plane if we know the normal vector n to the plane and the distance d of the plane from the origin. The equation of the plane, in this case, is called the normal form of the plane. We can also determine a unique plane if the plane passes through a given point P and is perpendicular to a given vector n. A unique plane can be determined if it passes through 3 given non-collinear points A, B, and C. A special case of condition 3 is that the 3 given non-collinear points through which the plane passes are points A, B, and C, where the planes cut the x, y, and z axes respectively. Thus, in this case, the intercepts made by the plane on the 3 axes are given, and the equation of the plane is called the intercept form. In this module, you will learn about the normal form of the equation of a plane and the equation of a plane passing through a given point and perpendicular to a given vector. Let us start with finding the vector equation of a plane in normal form. Consider a plane in a 3-dimensional coordinate system as shown. Draw a perpendicular from the origin to the plane. Let this perpendicular meet the plane at point P and be represented by vector OP. Let the perpendicular distance of the plane from the origin, or the magnitude of vector OP, be d. Note that here, the value of d cannot be 0. That is, the plane does not pass through the origin. Let the unit vector in the direction of vector OP be vector n. Thus, vector OP is equal to the length d multiplied by unit vector n. Let this be equation 1. Let Q be another point on the plane having position vector r. Thus, vector OQ is equal to vector r. Let this be equation 2. Let us draw vector PQ. Vector PQ lies on the plane and vector OP is perpendicular to the plane, which implies that vector OP is perpendicular to vector PQ. Since vector OP is perpendicular to vector PQ, their dot product is equal to 0. Let this be equation 3. Applying the triangle law of vector addition to triangle OPQ, we get vector PQ is equal to vector OQ minus vector OP. Substituting the values of the position vector of point Q and of vector OP from equations 1 and 2, we get vector PQ as shown. Substituting this value of vector PQ and the value of vector OP from equation 1 in equation 3, we get the result as shown. We already know that the value of D is not 0. Thus the expression reduces to the dot product as shown. Simplifying the dot product, we get that the dot product of vector r and unit vector n is equal to distance d of the plane from the origin. This equation represents the normal form of the vector equation of the plane. Let us now derive the normal form of the Cartesian equation of a plane. Let the coordinates of point Q be x, y, and z. Thus the position vector of point Q can be written in its component form as shown. Also, if L, M, and N are the direction cosines of unit vector n normal to the plane, then unit vector n can be written in its component form as shown. Substituting the component forms of vector r and unit vector n in the vector equation of a plane in normal form, we get the equation as shown. On simplifying, we get the Cartesian equation of the plane in normal form. If the direction ratios of the normal to the plane from the origin are given, then the vector and Cartesian equations of the plane in their normal forms are as shown. Point P represents the foot of perpendicular OP drawn from the origin to the plane. Let us learn how to find the coordinates of point P. If the direction cosines of normal OP to the plane from the origin are L, M, N, and the distance of the plane from the origin is D, then the coordinates of the foot of the perpendicular, that is point P, are given by LD, MD, and ND as shown. There is an infinite number of planes perpendicular to a given vector n in space. However, only one unique plane perpendicular to vector n can pass through a given point A. Let us find the vector equation of a plane passing through a given point A and perpendicular to a given vector n. Let vector A be the position vector of point A as shown. Consider another point P with position vector r on a plane as shown. Since points A and P lie on the plane and vector n is perpendicular to the plane, vector AP is perpendicular to vector n. This further implies that the dot product of vector AP and vector n is equal to 0. Let this be equation 1. Applying the triangle law of vector addition to triangle OAP and rearranging the result, we get the value of vector AP as shown in equation 2. Substituting the value of vector AP from equation 2 in equation 1, we get the vector equation of a plane passing through a given point and perpendicular to a given vector. Now, let us find the Cartesian equation of a plane passing through a given point A and perpendicular to a given vector n. Let the coordinates of the given point A be x1, y1, z1. Thus, position vector A can be written in its component form as shown. Also, let the coordinates of given point P be x, y, z. Thus, vector r can be written in its component form as shown. If the direction ratios of vector n are a, b, and c, then vector n can be written in its component form as shown. Substituting the component forms of position vectors r and a, and of vector n in the vector form of the equation, we get the equation as shown. On simplifying, we get the Cartesian equation of a plane passing through a given point and perpendicular to a given vector, as shown here. Consider 3 points A, B, and C in space. If points A, B, and C are collinear, then an infinite number of intersecting planes can pass through them. Thus, we cannot determine a unique plane in this case. However, a unique plane can be determined if it passes through 3 non-collinear points. Let us derive the vector form of the equation of a plane passing through 3 non-collinear points A, B, and C. Let vectors A, B, and C be the position vectors of points A, B, and C, respectively. Since the plane passes through points A, B, and C, they are coplanar. Thus vectors AB and AC lie in the same plane. Thus, the cross product of vectors AB and AC is equal to vector n, which is perpendicular to the plane containing vectors AB and AC. Let this be equation 1. Let P be another point on the plane having position vector r. We already know that the equation of a plane passing through a given point with position vector A and normal to a given vector n is given by equation 2. Substituting the value of vector n from equation 1 in equation 2, we get equation 3. Applying the triangle law of vector addition to triangle OAB and rearranging the result, we get equation 4. Similarly, applying the triangle law of vector addition to triangle OAC and rearranging the result, we get equation 5. Substituting the values of vectors AB and AC from equations 4 and 5 in equation 3, we get equation 6, which is the vector equation of a plane passing through 3 non-collinear points A, B, and C. Now, let us derive the Cartesian form of the equation of a plane passing through 3 non-collinear points. Let the coordinates of points A, B, and C be as shown. Consider another point P on the given plane having the coordinates x, y, and z. If the position vectors of points A and P are vector A and vector r respectively, then we can write vector AP as shown. Similarly, we can write vector AB and vector AC as shown. Substituting the previous values in the vector equation of the plane passing through non-collinear points A, B, and C, we get equation 7 as shown. Converting equation 7 into a determinant, as shown here, we get the Cartesian form of the equation of a plane passing through 3 non-collinear points A, B, and C with the given coordinates. Consider 2 planes pi1 and pi2 intersecting at a line, as shown. Now, consider another plane, pi3, passing through the line of intersection of planes pi1 and pi2. We will first derive the vector form of the equation of plane pi3 passing through the intersection of two given planes, pi1 and pi2. Let the normal form of the equation of plane pi1 be given by equation 1. Here, vector r is the position vector of a point on the plane. Vector n1 is the unit vector along the normal to plane pi1. And d1 is the distance of plane pi1 from the origin. Also, let the normal form of the equation of plane pi2 be given by equation 2. Let A be any arbitrary point with position vector A on the line of intersection of planes pi1 and pi2. Since point A lies on both the planes pi1 and pi2, its position vector must satisfy both equations 1 and 2. This gives us equations 3 and 4. Combining the equations of planes pi1 and pi2 for point A, we get equation 5. The line of intersection of planes pi1 and pi2 contains an infinite number of points. For any such point with position vector r that satisfies the equations of both planes pi1 and pi2, we can rewrite equation 5 as equation 6. An infinite number of planes can pass through the line of intersection of planes pi1 and pi2 for different values of the scalar lambda. Now, we will derive the Cartesian form of the equation of plane pi3 passing through the intersection of planes pi1 and pi2. Let the values of position vector r and normal vectors n1 and n2 for planes pi1 and pi2 be as shown here. Substituting the values of position vector r and normal vectors n1 and n2 in equation 6 and simplifying, we get the Cartesian form of the equation of a plane passing through the intersection of two planes. Consider two lines L1 and L2 in space. Let L1 be represented by equation 1 as shown. This implies that line L1 passes through a point, say P, with position vector A1 and is parallel to vector B1. Similarly, let line L2 be represented by equation 2 as shown. This implies that line L2 passes through a point, say Q, with position vector A2 and is parallel to vector B2. This further implies that vector PQ is equal to position vector A2 of point Q minus position vector A1 of point P. Let this be equation 3. If the given lines L1 and L2 lie in the same plane, then the cross product of vectors B1 and B2 will be a vector n, which will be perpendicular to the plane and vector PQ. This leads us to the condition for coplanarity of lines, which states that the given lines L1 and L2 are coplanar if and only if vector PQ is perpendicular to the cross product of vectors B1 and B2. We know that the dot product of perpendicular vectors is 0. Hence, the dot product of vector PQ and the cross product of vectors B1 and B2 is 0. Let this be equation 4. Substituting the value of vector PQ from equation 3 in equation 4, we get equation 5, which states the condition for the coplanarity of lines L1 and L2 given in vector form. Now, let us derive the condition for the coplanarity of lines L1 and L2 in Cartesian form. Let the coordinates of points P and Q be as shown. Thus, we can write vector PQ as shown. Let the direction ratios of vectors B1 and B2 be given. Using the given direction ratios, we can write vectors B1 and B2 as shown, substituting the values of vector PQ and vectors B1 and B2 in equation 5. We get equation 6. Converting equation 6 into a determinant as shown, we get the condition for the coplanarity of lines L1 and L2 in Cartesian form as shown. Consider two planes pi1 and pi2 as shown. Let the normal forms of the equations of planes pi1 and pi2 be as shown. Vectors n1 and n2 in the equations of the planes are normals to the planes pi1 and pi2, respectively. The angle between two planes pi1 and pi2 is defined as the angle between their normals n1 and n2. The acute angle between the normals is represented by theta and is taken as the angle between the planes. We already know that the scalar of dot product of vectors n1 and n2 with angle theta between them is equal to the product of the magnitudes of vectors n1 and n2 and the cosine of angle theta. Rearranging the terms of this equation, we get the cosine of angle theta between planes pi1 and pi2 with normals n1 and n2 as shown. If planes pi1 and pi2 are perpendicular to each other, then cos theta becomes 0. Substituting this value in equation 1, we find that the two given planes are perpendicular if the dot product of their normal vectors n1 and n2 is 0. If planes pi1 and pi2 are parallel to each other, then cos theta becomes 1. Substituting this value in equation 1, we find that the two given planes are parallel if the dot product of their normal vectors n1 and n2 is equal to the product of their magnitudes. Now, consider the Cartesian equations of planes pi1 and pi2 as shown. The angle theta between planes pi1 and pi2 in this case is given by equation 2. Note that here A1, B1, C1 and A2, B2, C2 are the direction ratios of the normals to planes pi1 and pi2, respectively. If planes pi1 and pi2 are perpendicular to each other, then cos theta becomes 0. Substituting this value in equation 2, we get the condition to verify if the given two planes are perpendicular. If planes pi1 and pi2 are parallel to each other, then cos theta becomes 1. Substituting this value in equation 2 and simplifying, we get the condition for two planes to be parallel. Consider a plane pi1 and a point A in space. We will derive the formula to find the perpendicular distance between point A and a plane pi1 in both vector and Cartesian forms. Let us start with the vector form. Let vector A be the position vector of point A with respect to the origin. Consider the normal form of the equation of plane pi1 given by equation 1. Distance d in the equation is the perpendicular distance ON1 of plane pi1 from the origin in the direction of unit vector n. Now consider another plane pi2 parallel to plane pi1 passing through point A. Since plane pi2 is parallel to plane pi1, unit vector n, that is perpendicular to plane pi1, is also perpendicular to plane pi2. Thus the equation of plane pi2 perpendicular to vector n and passing through a point with position vector A is given by equation 2. Simplifying equation 2, we get equation 3. Comparing equation 3 with the standard normal form of the equation of a plane, we find that perpendicular distance ON2 of plane pi2 from the origin is given by equation 4. Let us draw a perpendicular from point A meeting plane pi1 at point B. The distance of point A from plane pi1 is equal to distance AB. Since the planes are parallel, all perpendiculars between them will have the same length. Thus, distance AB is equal to distance N2, N1. Distance N2, N1 is equal to distance ON1 minus distance ON2. Next, we substitute the values of distances ON1 and ON2 from equations 1 and 4 in the previous equation. Equation 5 gives us the formula for the distance of a point with position vector A from a plane at a perpendicular distance d from the origin. Now, let us look at two special cases. In the first case, let the equation of plane pi1 be given in terms of its normal vector n and distance d from the origin. If the equation of plane pi1 is of the form shown, distance AB is given by equation 6. In the second case, we consider the scenario when point A coincides with the origin. When point A coincides with the origin, its position vector A becomes 0. Substituting vector A as 0 in equation 6, we get equation 7, which gives the perpendicular distance of the plane from the origin. Now, let us derive the equation for the distance of point A from the plane pi1 in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus we can write the position vector of point A as shown. Similarly, if the equation of plane pi1 is given in Cartesian form, the normal vector n to the plane can be written as shown. Substituting the values of position vector A and normal vector n in equation 6, we get equation 8 that gives the perpendicular distance of point A from plane pi1. Consider a plane pi and a line L as shown. We will derive an equation to find the angle between them. Let vector n be normal to the given plane. Let the angle between the given line and the normal to the given plane be theta. Let the angle between the given line and the given plane be pi. Angles theta and pi are complementary angles. Thus, the angle between a line and a plane is complementary to the angle between the line and the normal to the plane. Let the equation of the given line L be as shown. Also, let the equation of the given plane be in the normal form as shown. Then, angle theta between the given line and the normal to the plane is given by equation 1. Since theta and pi are complementary angles, cos theta is equal to sin pi. Thus, we can replace cos theta by sin pi in equation 1. Thus, angle pi between line L and plane pi is given by equation 2 as shown.